and or exercise, this is a finite dimensional vector space for the varieties that we are going to care about, moduli space curves. Okay, great. So those are cycles and numerical equivalents. Given a cycle or a class, an effective decomposition is, well, these things are already sums of subvarieties. So if my sum is written such that all of my coefficients are positive and all of my classes can be represented by honest-to-God irreducible subvarieties, then we're going to call this an effective decomposition. And it's just somehow one of the very nice ways that you might be able to write something. And if you can find an effective decomposition, we'll say the cycle or the class is effective. And so the fact that we have the word if here should imply to you that not everything is effective. And so like the obvious effective things are subvarieties themselves and silly sums of subvarieties where you just add 3 times one subvariety plus another subvariety. But there are other things where they may not naturally be presented in this way. They might come out with minus signs in nature the way they're handed to you, and you might have to work to try and find a way to express it as in a form of positive weighted things. So I'm not claiming this is unique or anything like that. It also sometimes doesn't exist. Okay, so effectiveness or effectivity, one of the two. Being effective is closed under taking sums, kind of obviously by the definition, or multiplying by positive real numbers. And what this means is that if you take all of your effective classes of a given codimension, they form a cone in the vector space. And this cone, it's a convex cone, this cone is the effective, or the cone of effective classes of codimension K. And an annoying thing that you're going to see in the talk is that if you look at the title of this slide, it says effective cones, which is not right. It should be cones of effective classes, but everyone calls them effective cones, and so we're going to do that too. The adjective effective just goes wherever it wants. But anyway, it's a cone of effective classes. Okay, and how do you understand cones? You understand the rays that generate them. If I'll have a picture in the next slide, but you want to understand cones by knowing their extremal rays. Well, we know that rays in this cone correspond to classes, and so the classes that correspond to the rays are called extremal. And here we'll have a picture. So here's a polyhedral cone. We can see it has 6 extremal rays. Those are the sharp corners. Boom, that green thing is one of them. And you can think about how to define these. It takes a little bit of, there's several definitions that might work, but the one that turns out to be nice for us is that a class is extremal if it has only the trivial decomposition. And what you can think of is if I'm anywhere else in this cone, if I was the inside of the cone, right in the middle, the north, the positive z-axis, I could take the sum of opposite rays here. I could take this ray and this ray, add them, and I would be along the positive z coordinate. So that is not extremal. It's in the inside. And similar for a face, I could take 2 kind of these adjacent corner rays, add them, and I'd be on the ray in the middle of the face. And again, that's not what we want. So the way we're going to specify this is if the only way I can add and end up on this ray is if I started there. And what that corresponds to, if you unwrap it, is the only effective decomposition is the trivial one. So the classes that you put are maybe multiples of themselves, of the class you care about. And so you say, okay, great, this is awesome. Look, we have this nice polyhedral cone, and we'll just check for all of the extremal rays, and then we'll be done, and we'll know it. But I use the word just. We'll just do that. And we should never use the word just, because the world isn't that nice. Because sometimes we have rounded cones, and it turns out everything on the edge is extremal for rounded cones. So the polyhedral situation is somehow represented by something very nice. Everything's finite. You could count it very easily. Look, it's so pretty. And then in the rounded case, you have infinitely many of these extremal rays. Now, knowing all the extremal arrays still tells you everything about the cone, so the goal is still an admirable one. It's just not as easy. Okay, so here we go. Here's the word in green, extremal. This is our definition that we're going to care about today the most. So if I can only give it a trivial effective decomposition, the class is extremal. Okay, great. Moduli of curves. I don't know who's all in the call, but I do know this is the last fragment of the semester, and so I'm not going to give the definition of MGN bar. I'm going to just make sure our terminology and notation are synced up, and if you have specific questions, of course, please let me know. First off, we're going to be using the Deligne-Mumford-Knudsen compactification by stable curves. That's MGN bar, as usual. And then the only thing I really need to clarify for you is two notational things. One, I'll use forgetful morphisms as usual, pi sub I. We'll forget the ith marked point. And boundary divisors. So I'm going to use this notation where I have delta sub h comma s. H is a number, it's an integer between 0 and g, and s is some subset of 1 through n to determine my marked points. Here's a picture. I'll represent boundary divisors as dual graphs. Think of them as just being in correspondence, because that's what we usually do. So this dual graph corresponds to the boundary divisor in my notation, delta sub 0, and then the set 1, 2, 3, because the rational component, which has genus 0, has the marked points 1, 2, and 3. Or you could prefer to think about the genus 2 component and write it as delta sub 2, 4, 5. And neither of these is enough information unless you tell me that I'm in, like, what space I'm in as well. Because if you only see 0, 1, 2, 3, of course you don't know that 4 and 5 are also floating out here. So this should be pretty standard, but there's a few different debates on what is best to use. This is what I'm using. Okay, some more terminology. Strata whose dual graphs have no H1, so have no cycles, are said to be of compact type. This strata is not an example because it has a cycle in it. Okay, so this is not of compact type. And then strata of compact type where all the genus is concentrated in a single component is said to be of rational tails type. And so again, here's a non-example. I have my genus split between, or I have two different components that each have higher genus. And so that's not rational tails type. Whereas the first one on the page is of rational tails type. So these are rational tails strata. And this one is a divisor, but of course you could break down into farther. And as long as there's just one kind of anchor vertex with all the genus, still rational tails. Okay, so there's our intro to moduli of curves. And to make sure we're on the same page, what do we know about effective classes, effective cones on the moduli of curves? So here we go. For one, in genus 0, M0 and bar is what's called a Mori dream space for n smaller than 6. It's explicitly known not to be a Mori dream space for n at least 10, which the fun fact there is it was first proven for n at least 134. And then it was taken down to 13, and then finally, not finally because we're not done, but more recently down to 10. And we don't know for 7, 8, and 9, which is remarkable that we don't know something about M07. Like, that's crazy, right? It's so, it's great. It's great. It's wonderful. Anyway, so what is a Mori dream space? A Mori dream space is, in a very hand-wavy type way, it's something where the effective cone of divisors looks like the polyhedral situation. And this is called a dream space because if you're doing Mori's minimal model program, these are the nice, this works really well with the minimal model program. And so you understand how to run the minimal model program on these dream spaces, so-called. So in other words, for marked 0.6 and fewer, these guys behave really well for the minimal model program. For 10 and above, not so much. Okay, you might ask about higher genus. Oh, okay, question from Adam. Quick explanation why n equals 1 through 7 has remained elusive. Oh, got it. So 7, 8, and 9. Great question. So for one thing you can show is if you know M0 n bar is not Maury dream space, then for every n above that n that you also know it fails using the forgetful morphisms. Basically, if M010 fails, then so does M011, and so on and forth. But you don't know the opposite, of course. You don't know, if it works for 6, you don't know that it works for 7. And so knowing that it works for 6 was a very explicit computation by Hassett and Schinkel, where they just literally computed a bunch of things, and they figured out the entire effective cone, and that's what it was. And it was doable because it was small space, because 6 is not that many points. For 10 and above, to bring it down to 10, they use some Brill-Noether theory, and the numerics of it, there's a bunch of this combinatorics that goes into it, and the numerics of it, you have to use these weighted projective spaces such that the weights add up to a certain thing, and there's these conditions that just 10 is the lowest you can go on that. And it comes down to literally just looking at the combinatorics of that paper. And so it's expected that just entirely different techniques are going to be needed for 7, 8, and 9. But of course, if you get 7, you get 8 and 9 as well. So that's a hope. And there was a recent paper by one of the finishing PhD students at Northeastern, actually, a couple months ago, that showed that M07 bar blown up at a very general point is not Maury dream. So that's not quite there, but it's very close. It's very, it's close. And you would expect, it's tantalizing because a blow up is just adding one extra divisor, And if you're looking at the cone of divisor, it's just one little thing. And yet it blows up. And so you'd say, oh, well, maybe, but no, we haven't been able to yet. So there's work on it, but entirely new techniques are needed in some respect. And so we just don't have it yet. Sorry, that was maybe too long for a quick question, but.
Cool. Thanks, Vance.
Yeah. Excuse me. So yeah, in higher genus, we know that, okay, so in genus 1, if we have at least 3 marked points, then the effective cone of divisors is not rational polyhedral, so it's rounded at some point. So in particular, it's not Maury dream. And ditto for all higher genus if you have at least 2 marked points. And the first is by Dawe and Izette, and then the second here is by one of Dawe's students, Scott Mullane. And that was just like this year, so fresh. Oh, and I'm not clicking right, there we go. Some other things we know. The hyperelliptic loci are of various flavors are extremal in their cones. We don't, and the fact that I'm leaving out a bunch of hyperelliptic loci doesn't mean they aren't, it means we don't know if they're extremal or not. The virus-Strauss divisor in low genus is extremal, and this is Rula, Jensen, and Jensen. Certain pinwheel strata in genus 0 and genus 1, and pinwheel strata are just particularly nice rational curve strata. Certain genus 1 codimension 2 pinwheel strata are extremal. Every codimension 2 stratum of Mg and M0n. And then the codimension 2 cones for genus 1, genus 2 with sufficiently many marked points have infinitely many extremal rays. So in particular are, you don't use Maury dream space when you're talking about higher codimension things, but they're the rounded type cones as opposed to the polyhedral ones. Excuse me. Okay, so one thing you might notice here is there's kind of 2 directions that this study goes. One is to look at a particular cone. So fix my favorite space, M0 n bar, and say, what is its cone of divisors or its cone of codimension 2 or whatever? What does this fixed cone look like? Is it infinite? Is it whatever? Or infinitely generated? Whatever. The other direction you could go, which is kind of like bullet 3, bullet 4, and bullet 5 and bullet 6, is looking at families of classes throughout a wide variety of cones and saying, are these extremal in whatever cone they live in? And kind of the ethos there is often geometrically interesting classes like hyperelliptic loci end up being extremal, and vice versa. Extremal things can be geometrically interesting. So there's, again, two directions: fix the cone or fix the family that you care about. And this thing I'm going to talk to you about today is really the second kind. I'm looking at a family of things and letting the cones be whichever cones they need to be. Cool. And you also notice there's a bunch of work in divisors and a bunch of work in higher codimension classes. And we're going to be doing higher codimension stuff. So, okay, we're now to the technical bits. And again, some of these results that you saw on the previous slide are for divisors. And it turns out there's a nice bit of technology for divisors. If you have a irreducible effective divisor in a projective variety X, then there's a really easy numerical test to see if that divisor is extremal. You find some curve that lives in it and is a moving curve, so its deformations cover the divisor. You intersect, get a negative number. If you get a negative number, then your divisor is extremal. And this lends itself actually really well to moduli of curves, because what do you do if you have a divisor? You have two components, genus 1 component, genus 2 component, say. Fix those components, but then slide the node around. Okay, that defines a curve in the moduli space. And that curve lives in the divisor that you get by thinking of this picture as like a dual graph. And it turns out that intersection is very easy to compute. And that works for getting a lot of the boundary divisors. And you can do other more clever things in other situations, but this works for that. It's really nice. It's really not it's a good exercise in like intersection on moduli of curves. So that's great. Another thing you can do is you can find a map from your space X to a new space W. Now you want that map to be a birational morphism. And then you want your divisor that you care about to be contracted by that birational morphism. And there you go. Now you know that the thing that got contracted, that was an extremal class. That was an extremal divisor. So these are two things that you can do for divisors that end up being very useful. Yeah, but here's another bit. Here's another technical bit that we're going to use today. Oh, sorry. Open question. Does this intersection calculation with the negative intersection, moving curve, blah, 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 generalize to higher codimension cycles? This is an open question. No one has an answer for it. All the obvious things you would try fail very quickly for lots of reasons. And so it's not clear how to fix that. And so the failure of this lemma to generalize makes higher codimension cones significantly harder. And you need quite a bit more technology to deal with it. But here's one that's also useful for moduli curves. So this is one that I actually proved in this paper that's inspiring this talk. So I'm happy with it. But if you have X and Y projective varieties and you have an extremal class in one of the varieties, then the product of that class, or that cycle, that subvariety, with, so I should just read it. Z cross Y is extremal in X cross Y. Okay, so you can, extremality plays well with products. And if you know anything about moduli curves, this is exciting because boundary strata are products of smaller moduli spaces. So there's some hope that you can maybe use some extremality stuff, push them around within each other, and start getting extremality of boundary strata within other boundary strata. And in fact, that's exactly what we're going to do. So if delta is some boundary strata, and I don't necessarily mean a divisor, I just mean any stratum, and delta prime is another boundary stratum such that delta is contained in delta prime, so maybe delta prime you get by smoothing one of the nodes, then the higher codimension one is extremal in the lower codimension one. And the idea of the proof is, okay, so suppose there's one codimension off. So I have a codimension 2 stratum living in a codimension 1 stratum. Well, you can write the codimension 1 guy, or the codimension, smaller codimension guy, as a product of moduli spaces. And then think of the other one as that same product, except at one place where you've added an extra node, right? And now you view this this new product, GA, GN, GB, GNB. Oh, okay, I said that wrong, but this thing that I'm circling. You view that as a boundary divisor in MG1N1. But now we know that boundary divisors are extremal. And we know that products, Cartesian products, play well with extremality. And so we're done. If you're not codimension, if it's not a codimension 1 degeneration, you just iterate this argument. And if you want, put a little asterisk by this idea, because at the very end of the talk, I'm going to tell you why this is it is not quite fully honest. There's something wrong with this, and it's stopping certain things from working, and we'll talk about it at the end. But this is the idea of the proof, and this is so this is nice. Okay, so those are the technical bits. We're now going to get to the really technical bits, and this is kind of the meat. This is the big idea that makes a lot of it work, but it's a little bit of a pain. So bear with me. I have a picture coming that's going to make it all much better. So first, a definition. If we have a morphism between varieties, f from y to x, and a subvariety in y, then we can define the index of the subvariety under the morphism as basically the dimension drop. So the index should tell you how much the dimension fell by applying the morphism of the subvariety. Okay, so yeah, before I write this lemma, note, easy consequence. The index is positive if and only if z drops in dimension. Otherwise, it's 0. Okay? Okay, here's the technical lemma. And it's a bunch of words, but we're going to get to a picture, I promise. So here we go. Let gamma be a map from y to x, and f another map from x into a third space y, or w. Let them be morphisms of projective varieties, and assume that the exceptional locus of f is contained in gamma of y. If we look at the restriction of the push forward to the effective cone, and we request that that restriction of the push forward is injective, okay, we're going to assume it's injective, then if we have an extremal subvariety in y, and if the index is positive, then the image of the subvariety, the class of the image of the subvariety is extremal in X as well. Okay, this is a huge bunch of nonsense. We can make it a little easier with this remark. If gamma's inclusion, then the restriction of the push forward is automatically injective. And so we can just focus on situations where we have subvarieties of subvarieties of subvarieties. And so hopefully the idea now that you're getting based on the previous slides in this is that, oh, look, I have strata which are extremal with another strata which are extremal with another strata, and you're seeing this tower of extremality that we're going to be pushing into the full moduli space. Okay, here's the picture for the lemma. Suppose I have some variety y, and z is extremal in it. Green means extremal. I can put it into x, and then I can contract y. And if I can do this, and we'll notice as well that z dropped dimension. It was dimension 1, now it's dimension 0. So my E sub f is positive. If we assume this and that the technical bit about being injective, then this image down here, this green image stays green. It didn't have to turn blue or something because it's still extremal in x. Now this, I guess, actually this should be w. Sorry, forget that x. But this green thing remains extremal. So this will be a boundary strata. This will be a smaller boundary strata. X will be the moduli space of curves. And then we're going to get what we want. So let's put it together. We'll let delta be any boundary stratum you want. here's the flow of the proof based on the previous slides. I'm going to put it all down for you. Well, if delta is divisor, we're done right away. So let's assume it's not. If it's not, it's contained in a boundary divisor. And by earlier comments, it's extremal in that boundary divisor. So what we need to do now is find some f from mgn bar to w such that the exceptional locus of f lives in or is equal to the boundary divisor that contains the boundary stratum we care about. And we need to make sure that the index is positive. And if we do all of that, we can apply the technical lemma, the very technical lemma, and we're done. Bada bing, bada boom. Now, such a setup comes very naturally from some of our favorite alternative compactifications of MGN. Hassett spaces, woo! Yeah. So, great. W is going to be a Hassett space, F is going to be a reduction morphism. What are those? Great question. Hassett spaces are a modification on moduli spaces of the usual Deligne-Mumford compactification, where all this technical gook is telling you that we allow certain points to come together if the weight associated with them is small enough. So you get to pick weight data, which is this A, and then you allow things to collide as long as the total weight at that collision point remains small enough. So these gives us different compactifications. There we go. Sometimes called moduli spaces of weighted stable curves, developed by Brendan Hassett in 2003. And so that's our W. And our F, the morphism from MGN to W, is what's called the reduction morphism. And all it does the obvious thing. It takes your curve with its mark points and it throws the weights on there. So it reduces the weights to whatever we pick them to be and then stabilize if necessary. And the upshot of this is that the exceptional locus of the reduction morphism consists of curves in MGN bar that have a rational tail with at least 3 marked points of total weight at most 1. Okay, so these reduction morphisms exactly kill a bunch of boundary divisors, is the long and short of it. So as an example, if our weights are all 1/4, then the boundary divisor where I have a genus G component with no marked points attached to a rational component with all 4 marked points, that's exactly the exceptional locus of that reduction morphism. And recall from a few slides ago, we actually had to do 2 things. We had to find that morphism, and we had to show that the index is non-zero. And the other nice thing about Hassett spaces and reduction morphisms is it's super easy to calculate what your index is. Okay, so here's another exercise. If you have all diagonal weights, then if delta is a boundary stratum, then the index is non-zero if and only if there's a rational tail somewhere in that stratum that has moduli, so has more than 3 special points. Exercise. Okay, this works. Yay. So the setup works, assuming we pick our weights correctly, which we don't even have to be super careful about it. It's pretty cut and dry what you should pick. And this gets us the majority of the rational tail boundary strata. So this doesn't get everything, but it gets everything. It gets a lot of things, right? It gets anything basically that lives in one of these contracted guys. Excuse me. It works usually. So there's a bunch of situations it doesn't work in, right? There are some limitations. And the biggest one is that we can only handle strata with at least 1 rational tail with moduli. So this exercise is exactly the failure of this program to generalize to every boundary strata. And so that turns out to be a lot of them, right? Like most of the compact type ones and anything in the irreducible divisor. But if we're hoping for a reasonable goal that we can talk about in the course of an hour, maybe we'll shoot for just getting all of the rational tail strata. Like, let's just aim for that right now. So what sort of things are we missing? We're missing things where we have rational tails coming out, but they have only enough marked points to be stable, and they don't get any extra moduli from them. So, side note, this was my favorite part of working on this project, is that I kept calling it rat tails, which are really awful haircuts. And yeah. Anyway, we're getting rid of all the rat tails. So I'm gonna give you a representative example to show you how we kind of get the rest of the things that we couldn't get with the general setup. And it turns out that this is a huge pain in the butt. But I'll give you the nicest kind of sub case, and we'll see a rough idea of how it goes. And then for the details, you can look in the archive paper that this is based on. So here's an example of something with no moduli on its rational tails, right? This is an M03, this is an M03. And so if you just covered up everything but this genus G component, you would be the same dimension as this stratum is overall. And what that means is that your index is 0. And so although you can have a Hassett, excuse me, a Hassett space that contracts 1, 2, and 3, all the marked points are all, weight 1, 3, and they come together, but this doesn't lose dimension. And so its index is still 0. And so we can't apply the technical lemma from before. But okay, we can do something else. And here's what it is. So note that this is, by all the previous work, this is extremal in the divisor where I put 1, 2, and 3 all just on the same rational component. So if I shrink this node, shrink this edge, I have 1, 2, 3 all living here, then that contains this stratum, okay? So let's write this stratum, this is delta, so let's write it as an effective decomposition. So we're gonna write it as some classes plus some other classes living in n to the 2 of mg, I guess 5 in this case. And what are my e's and f's? Well, all of my e's, whatever they are, there's some irreducible subvarieties in mg5 bar. Don't know what they are, but whatever they are, I'm gonna request that they survive push forward by pi1, pi2, and pi3. So they should not vanish when I push them forward. And I'm gonna request that the f do vanish, that they don't survive push forward. And so, Vance, you forgot some cases, you might say to me. What about if there's some class that's in the decomposition that only survives one of the push forwards and not the other two, or two but not the third? And it turns out that can't happen. So you either survive all 3 of them or you survive nothing. Okay, so it really is, it's an all or nothing situation. So we're gonna have you either live or you die under push forward. And that's exercise, easy exercise. Draw the commutative diagram and you win. Good, so we have this set up and then push forward. Oh, that's a lot in one push forward. So when we push forward, what do we get? Well, when we push forward delta, we're gonna get either delta 0, 2, 3, delta 0, 1, 3, or delta 0, 1, 2 in mg4, right? Because what happens? If I kill 1, then these guys move down by stabilization. If I kill 2, then 3 moves down to be with 1 by stabilization. If I kill 3, 1 and 2 come down to live together on the rational component. And so when I push forward the left-hand side, I get one of these 3 classes. And I push down the right-hand side, the F's all die, and the E's become whatever they are. Push forward of E's, but they don't die, they live. But now, okay, this image on the left, it is a divisor in mg4. Therefore, it's extremal. We've already shown that. And so these push forwards of E's, all of these classes are actually proportional to the divisors. And because they survive all 3, it means they're proportional. The push forwards are proportional to all 3 divisors. And so you conclude is that every E sub S, every subvariety in this sum, has to be in the preimage of pi1 by this divisor, pi2 by this divisor, and pi3 by this divisor. Okay. Cool. So you at least know where E1 lives. But now, hey, we have a moduli space. And so we can take a modular interpretation of things. And so by modularity, what we can conclude, because of the way these three preimages intersect, E, in fact, all of the E's, have to live in this specific divisor up in MG5. So they have to have a genus G component with a 4 and a 5, and they have to have a rational component 1, 2, 3. They have to live in that divisor, all of the E's. Okay, now we're going to take our original sum up here, and instead of thinking of it as a codimension 2 class on MG5, we're now going to write delta as a codimension 1 class in that divisor, in that boundary divisor. Well, all of the E's we concluded already were in that divisor, so nothing about them. They're fine. They come along for the ride. The F's that we thought about earlier, some of them might live in the divisor, some of them might not. And so that's the tilde. Some of them we include, some of them we don't. If they're in the divisor, good, they're, and if they're not, don't write them. But, haha, we now have a stratum in a boundary divisor, and we know that this stratum is extremal in this boundary divisor. And so everything in this effective decomposition has to actually be proportionate to delta itself. So even though I wrote all these E's thinking they might be random classes that are adding together in the right way, no, false. They were all delta the whole time. Maybe with a half in front, or a third in front or something. But they're all just little copies of delta. So this is a stupid decomposition. Like, why, that I was trying to find a non-trivial decomposition. Okay, so all of these are proportional, and so let's subtract and rescale. Right? From my original guy here, I'm going to subtract all the E's over because they're actually just copies of delta. I'm going to subtract some of the F's over because they're copies of delta. And what we end up with is now, and rescale, so delta is equal to some of the F's. Because remember, some of those F's might not have been in delta 0, 1, 2, 3. They might have been just some other classes. And so I can write this back in my original codimension 2 cone on MG. That should be a 5, MG5 bar. But now I have a class that survives push forward by, for example, pi1. And I have classes that were defined to not survive push forward by pi1, right? And that's a contradiction. I can't push forward the left-hand side and survive and the right-hand side and die. So what that means is that at the end of the day, I must have started with a trivial decomposition. There were never any F's. And in fact, there were never any E's, there were just deltas in disguise. And since that's the only decomposition I can have, it's extremal. Cool. So now you have to generalize this to all different cases, which gets a little harder, but is doable. And then you do a couple inductive arguments and you get everything. So theorem, all rational tail strata in MGN bar are extremal in their respective cones. As a really nice corollary, all strata in M0N, all strata are extremal because all strata are rational tail strata. And we didn't actually use anything with the genus at any point in here. As a side note, this was expected, but still worth checking because there's a remark that's off the page. Okay, so because if you take, instead of M0N bar, if you take M0N with a tilde above it, i.e. you take M0N bar and quotient by the symmetric group, by Sn, now you can't tell P1 and P2 apart anymore. So if you swap these two, that's actually the same point in the moduli space. That space, you can also ask about its effective cones and stuff like that, and people have, and not all boundary strata are extremal in the symmetric quotient, which is surprising. We found out via direct computation in M07 tilde in 2017, I think, Hanbin Moon, computed some F curve. Oh no! Oh yeah, it's cut off. The remark's cut off. Yeah. Yeah, there's some really interesting stuff involving F curves that you get some unique relations that you wouldn't maybe expect. So although this was expected, it is worth checking because again, the remark that we cannot see says that it's not true in another place we expected it for, in a very related space where you quotient by Sn. Okay, so this framework, we made some very specific choices. We picked Hassett spaces, reduction morphisms, we picked a lot of things. So what extensions can you get from this that, you know, I trimmed it down for the sake of the talk, but what can you actually get from it? And so one thing you can get without even trying is what I call dangling rational tails. So it doesn't matter if you only have rational tails, it's just if you have a rat tail anywhere, and it has moduli, that's good enough. And you can do the same process that we did before. If it doesn't have moduli, maybe, depends. It's case by case at that point. But if it has moduli, dangling rational tails with moduli, you're good. Also dangling elliptic tails, lots of danglers. And what this does is if you have an elliptic curve or a genus 1 component that has a node but no marks, then you can do a very similar process. Instead of using Hassett spaces, we use another alternative compactification of MGN called compactification by pseudo-stable curves, which contracts unmarked elliptic tails into cusps. And your index is positive there, and everything works basically the exact same. You just have to understand what pseudo-stable curves are instead of Hassett spaces. So that works too. Other miscellaneous boundary strata, just basically by coincidence, end up working if you have all your cards lined out right, but not in like a nice family that's easy to talk about in any meaningful way. And then the other thing that I haven't mentioned at all here is this cone lives in a vector space, and it's a real vector space because my coefficients are real, and you can take the closure of that cone in the usual real topology, and you actually pick up extra classes. You pick up things that were not effective, but now are in that closed cone. And so we call that the pseudo-effective cone. And it turns out that most of the results that I showed you go through exactly in the pseudo-effective cone. And so you know that these are not just extremal in the effective cone, you know they're extremal in the pseudo-effective cone. And that's actually significant because just because one's extremal in one or the other does not actually imply, I mean, there's no implication going on here. The pseudo-effective cone is its own weird beast. So we do get some of that. And for exactly what we get, exactly what transfers, you'll have to read the paper because I mentioned it there, but it's kind of not worth mentioning here. Still open in regards to this framework. There's a ton still open, but in regards to this framework, like this idea of how we do this, well, most obviously elliptic tails with marks because my pseudo-stable curves method needs them to be markless. More general strata of compact type. If I have genus 2, genus 1, genus 1 with marks randomly, I can't do anything about that. We need something that has a positive index type thing. Strata in the irreducible divisor. And here's where we mentioned the asterisk I put earlier, in that not all boundary strata are products of smaller moduli spaces. They're products of smaller moduli spaces modulo S2 sometimes. And I don't know how that modulo S2, how that quotient by S2 impacts things. There are some subtleties that go on with it that I'm working on but haven't worked out yet. So reducible divisor, if we get that, then we basically get everything. If we can understand the S2 quotient, then the story is all boundary strata are extremal. On the other hand, that would also be a natural place for a counterexample to come up. So that would also be interesting if that's the reason why certain things failed to be extremal. And then I picked the pseudo-effective cone for the still open as well, because it's super technical, moving moving from effective to pseudo-effective. And there's a series of 3 papers. Oh, I'm forgetting the names on it now, but there's a series of 3 papers that are just built around when can you extend. And they're all slogs, very technical slogs. And it's just a very delicate thing. And so not everything generalizes, even though some of it does. Okay, and that's it. I'm done.
Great. So let's thank Vance, and you can unmute yourself and clap, or emoticon clap. And let's open it up for questions.
Oh, I also have sources. But yeah.
So I have a question just to start. So for the case of elliptic curves with marks,
Yeah.
Can one, is it possible to combine kind of pseudo-stable and weighted spaces and contract them, or somehow weight 0 points not allowed in all this business?
Well, so that's a great question, and it's something I thought about, but probably haven't thought enough about. I don't know. And honestly, yeah.
Passive spaces with weight 0 points, they exist, but they become a lot more singular than, they're not normal. They have ugly singularities, and I don't know how if that kind of crashes what you're trying to do.
Because somewhere in the background of all this, in all the technical bits, is or even in the initial definitions, we are assuming our varieties that we're thinking about are either smooth or Q factorial, or just in general have mild enough singularities. And I don't know if weight 0 Hassett spaces are mildly enough singular. But that's a great question, and it's something that I want to think about something like that. I just haven't been able to yet. But excellent question. I don't know. And
so for the open cases, is your expectations that they are, or they extremo?
It's generally believed that they are. And in particular, the case where you might have guessed there's a counterexample, because we found a counterexample in M0n tilde, you would assume basically that any counterexamples would maybe be coming from that's the first obvious counterexample spot. And so the fact that we don't have counterexamples in genus 0 lends credence to the fact that you might not find any counterexamples. The other thing is statements like all codimension 2 strata are extremal. Well, okay, there's really, divisors are unique, but codimension 2 and codimension 3 are not that different. They are, of course, and there are some differences, but you really do expect that it's widely believed by pretty much everybody that we should have, everything should be extremal. Yeah. One of the nice things of working on this type of thing is, although it's widely believed, and so on that respect, it's not like surprising if you got that result, all of that technical framework works wildly generally and has nothing to do with moduli spaces. And so you can now start asking about the minimal model program or variations on it in higher codimension for anything where you have that set up. And so one thing that's nice about the boundary strata is they're a good testing ground for more interesting classes and more interesting spaces. But yes, it is believed that it should be an affirmative answer.
All right, thank you. Any other questions? Okay, if there's no other question, please, show your face so that Vance can see that he actually had an audience, and let's, wave at him one last time. There we go.
Good to see everybody.
All right.
Thanks for coming.
Thanks, Vance, and thanks everybody for coming. And this was the last fragment of the semester. So happy summer to everybody.
Stay well. Be safe.
All right. Bye.
Yeah.